Our final lesson on finding volumes of solids of revolutions with the disks and washer method. So now what we have to do is worry about what if we revolve this around not the x-axis or the y-axis, but something else. I call it an offset axis. Now these will all be horizontal or vertical. So we're going to do 3 examples with the same bounded region to begin with. So every time we're going to start with the same picture, we're just going to revolve it around a different axis and see what happens. And you're going to see real quickly how if you haven't been drawing the pictures, this is just brutal. You have to pay very close attention to the picture. And if you do that, you can get the equation. But otherwise, this is just a tough section if you have been ignoring the pictures. All right, so we want to get a very clear picture because it's so important. So I'm going to draw this. So I have my square root function. I have the x-axis, and I have x equals 4. So this is going to be our starter. That's our bounded region for all 3 examples for this lesson right here. Now I know this is at the 4, and I could see if x is 4, y is 2, so I know that top number, that's 2 on the y-axis. Now where am I revolving this around? The horizontal line, y equals minus 2. So if this is plus 2, this would be minus 2. Now imagine that. Instead of swinging this around the x-axis, this is the axis of rotation. So this will be reflected 2 units. So if this is minus 2, this would be minus 4. That would be this horizontal line. And then 2 units beyond that, at the minus 6, let's see here. Here's this reflected, here's this reflected, and then it goes from here, and this is going to be down at the minus 6. So that's all solid. And let's get a 3D effect going here. So I don't know if you know what a wing nut is. Like, this doesn't have it. This is kind of like something that would screw onto a bolt, right? So if I had a bolt right here, I could screw it in there, and it's like capped, like kind of like in the bathroom, the screws that like hold the stalls together. A lot of times the cap might look like this, and the screw goes into it. So it would just be that cap. What is the volume of this particular thing? Well, to find the volume, we need to take a slice out of it perpendicular to the axis of rotation. So that's going to be this way. So I'm going to draw this. So there's my outer one. There's my inner one. This gives me a feel for the thickness. See how that would be measured along the x-axis? That is a dx thickness. You always want to go, when you're looking at the radii, always go from the center of the circles up to the given drawn curves. Don't go to the reflect. Remember, this was what I started with, and this got reflected. So I want it for my radius. I want to go from here to the center. That's big R. And then from here to the center is little r. And now I have to carefully think about this. Well, look at my big radius. From here to there, this distance would be from 0 to the curve. That is root x. But I got to go 2 more units down. See, this radius is 2 units plus from 0 up to that function. So my outer radius is 2 and the function. Now in other problems we're going to subtract. You can't just oversimplify it and say, oh, always add them together. So you've got to really dig into the picture. And this, look at it, 2 and some more, 2 plus. All right, let's look at our inner radius, the small r. The small radius is always 2 units. See, the outer one tracks here along the curve, the inner one is always constantly this much, which would be 2 units. So the inner radius is constantly 2. Well, if you can see that, that is the hard part of the problem. Let's set up our integral. So the volume is pi times the integral from, this is a dx thickness. The outer radius, see I wrote it down, 2 plus root x squared, minus the inner radius, 2 squared, from 0 out to x equals 4. There's my setup. And you can tell the radii are the issue. If you're not drawing the picture, you're going to really struggle here. Even if you draw the picture, this is a section where people have lots and lots of questions. But look at it. 2 and from the distance from the x-axis up to the function. It's the distance to the function and 2 more. It's right stinking there in the picture. Once you get this, all you got to do is punch it in your calculator. I got 92 and or 92 and change units cubed. But this is the hard work. This is the heavy lifting. All right, we're going to do example 2. Remember, I'm going to use the same beginning region. We're just going to revolve it around different axes to see that you can't just slap stuff in and call it good. You've got to navigate the picture. I was going to say the photo. Ah, dang it. All right, so that was our boundaries, our root x, 0, and 4. I didn't want to erase that. But this time we're bounded by, or not, we're revolving it about y equals 6. Okay, the last time it was y equals minus 2. This sure feels like it's going to be similar. All I did was change that one number. Let's see how similar it is. Now, I already know how this is going to play out, so I'm going to draw it differently. You wouldn't know this right out of the gate. Here's my initial region. This is x equals 4. Here's y equals root x, and here's the x-axis. Same starter. And we already reasoned out that this would be 2. Now, the axis we're revolving it about would be 4 units above that, which is at the 6. This is my axis of rotation. Now, when I revolve it, I'm basically going to be reflecting this up here. So if this is 4 units, I need 4 units up. And then another 2 units, this would be up to the 12, right? So 0 to 6, 6 to, see. All right, so let's see. See this point right here? It's 4 units from the axis, so I'm going to go 4 on the other side. And that's going to complete that vertical line. This point is 6 units from the axis, so it's going to be all the way up here. And this is going to be the horizontal line, and that's got to make that same shape. So this is going to look different. So this is the solid portion of it. So this would look like a tire kind of shape, you know, like a cake almost. The edges are cylindrical, but the inside kind of bows inward, like this is a funnel shape on the inside, and there's a hole here, right? So you could actually, if I set this up right, you could pour stuff into it, and it would funnel right through there. And this is your solid region right here. It would extend into 3 space. Again, you might want to look at those videos that showed you the computer-generated version of what it looks like when you rotate them. Well, let's try to slice this. Here's the axis of revolution. Perpendicular to that, I would get a washer shape. This is the thickness. That's a dx thickness again. Now, I don't want to do my radius. This is the reflected part. I always want to do my radius down to the original drawn portion. So this is my outer radius. which notice is always 6 units. This is my inner radius, which this is a little harder. My inner radius, see how it's 6 here, but it shrinks? What I'm seeing is all of this 6 take away the curve. You got to take away the distance from the axis to the curve, and what's left is the radius of that washer. So let me try to use another color. This is the radius I want. See it? It's offset. It does not go from the axis to the curve. It's offset, hanging out in space up there. How do you find that distance? You know that that's 6 from 0 up. That is 6, and then you got to take away the distance to the curve. And when I take that away from the 6, see how that leaves that portion? This is 6. If I take away the distance from 0 to the curve, see how that leaves me with the radius there? So that's what it is. Now the last one we had to add. This one you got to subtract. See, if you're just guessing, if you're not looking at the picture, good luck with this. You've got to draw the picture, and even then it confuses people. This is an indirect way to get the radius. That messes with people. Well, if we could just take that for, okay, if you say so, or it'd be even better if you understand it, let's set up our equation. So I have pi integral larger radius 6 squared minus the inner radius. See, that's why I like to chunk it up. I do all my thinking, and then all I got to do is slap it into the equation. It is a dx thickness, and now my limits are on the x-axis because it's dx. The low is 0, and the high, right, it goes from 0 to 4. So that's the hard part, setting up that equation. From there you can plug it in your calculator, and when I did, I got 175.93, and that'd be units cubed. Well, we did 2 this way. I think we should spin one this way, and then I'll let you play around with this. Here comes example 3. This time we're going to revolve it about x equals 10. So not y equals, but x equals. Let's see. So there's my x and y axis. I know that my beginning region is the same one we've been working with. This is 4, this is 2. But now we're going to revolve it around x equals 10 is 6 more units out from there. So we are going to spin this around that central axis. So the way I would think about this is this part is mirrored 6 units on the other side. And then see how that's 4 more units to the end? So out to 20. I'm going to go down. So this is kind of like an umbrella pedestal. Like for outside, you know, like outside table, you got a little thing that holds the umbrella in place, it slides into. This is an open slot. This is weighted material to keep it from moving around. So that's kind of the look we have here. We're trying to find the volume of the solid, not the space inside, the solid part. Well, how do I do that? I have to take a slice out of this perpendicular to the axis of rotation. So here's my outer edges. Here's my inner edges. This gives it a little bit of a feel for the thickness. Notice that that is a vertical thickness, dy. This is my original image, right? So the outer radius, the larger radius, is there, except this is going to be a y. And my inner radius is here. Well, let's see if we can figure out what these are. The easier one is the inner radius. See how the inner radius tracks along this line so it's constant? So this was 4 and this was 10. That's 6 units. Look, there is no 6 there. That's the difference between 4 and 10. So good luck guessing that if you don't draw the picture. The large radius would be the whole distance, 10 whole units. See it right here? The whole distance. Take away this. The large radius is from the center all the way to the edge. Take back that much, which is the distance from the axis to the curve. So that's going to be 10 minus, I want to say root x, but it's got to be y stuff. If y equals root x, then x equals y squared. So this is going to be 10 minus y squared. 10 minus this distance is the large radius. And that distance is the square root of x, which is the same as y squared. That is the hard part. The volume of this thing is going to be pi times the integral. Outer radius, I already did that thinking, squared, minus inner radius, squared. This is a dy thickness. And so my y values go from 0 up to 2. If I can get that, which is a big if, I punch it in my calculator, and calculator says 254.68 units cubed. All right. Well, I can tell you that the quiz will not be all of these. These are the harder end of the spectrum. So you can expect to see, you know, some simpler ones, pure disc method, washer methods. Oh, excuse me. Both of those mostly off of the X and Y axis, the easier versions. But you can expect to see a little bit of these offset axes. So practice makes perfect. Let me know with questions through the email. You can take, sometimes it's hard to verbalize your questions, like to write them down. So if you want, you could take a picture and like, even like in the picture, like if you're stuck, you could put a little note like, I'm stuck here, and then just take a picture of that and send it to me, and I'll respond. Okay, work on it. The pictures are important, and we'll be talking.